Thank you very much. It's a great honor for me to receive this award from Mr. Nagamori and the Nagamori Foundation. I'm very appreciative of that, and especially because I can talk to you a little bit about what we have been doing about partial power converters and its application to energy transition. So this is just an outline of my presentation. I will first explain a little bit what partial power converters are about. And then I brought 3 examples in which we have applied this technology in photovoltaic energy systems, green hydrogen production, and electric vehicle charging infrastructure. But first, I would like to show you where we have been conducting this research. This is literally at the other side of the world, across the Pacific Ocean in Chile. It's early in the night over there. This is some photos of the day by day that we have there in our laboratories. So to understand what a partial power converter is, first have a look at a full power converter. A full power converter is a traditional power electronic circuit where power enters and power goes out. And because of that, we have some losses. This is very similar to the charger of your phone. So when your phone is charging, you feel the heat. Those are the losses. A partial power converter is a way smaller converter, and we have then a direct power flow path that doesn't go through the electronics. And because of that, we have fewer losses. It's also smaller, and it can also be less expensive. This is not new in the sense that this already existed for AC systems. If you see this wind turbine, this is a double-FET induction machine where you have a direct power flow path between the stator and the grid. And the power converter is just a fraction of the total system. So if you have a 3 megawatt wind turbine, you can control this with just 1 megawatt power converter. But this is for AC systems, and many of the energy transition applications use DC-DC converters. So the challenge was how to do this for DC-DC. In this case, I'm showing a small example on how the full power converter works by showing just the area of power conversion. So power is just voltage by current. And in this case, you can see here an area of 100 watts where you have 50 volts and 2 amps. That gives you the 100 watts. And if you want to convert this let's say, for a 32 volt output, then you would have this different shape and form. And we just assume for this example that we will have 4% losses. But if we look at the partial power converter concept and we overlap the input area with the output area, the overlap is actually something that doesn't need to be processed. And this can flow directly without processing to the output, allowing a way smaller power converter over here, just to convert this 34 watts into 33 watts with just 1 watt of losses, getting to 99% of efficiency. So to achieve this, we used high-frequency isolation transformers to produce something that we call an auto transformer, but with electronics, in which we can connect the input to the output to provide this bypass flow, shown here in green, and only processing the blue part that you see over here. Thus, we only have to process a very small portion of the power. We can make 4 types of power converters this way. 2 to elevate the voltage, which are shown here. And something very interesting to see is that when we go very close into the input and output voltage, they are very similar. We theoretically could go all the power process without processing, so having basically 0 power conversion. And then if you want to double the voltage, you would end up with this kind of structure with a full power converter. Anything in between is partial in ratio. We also have this to lower the voltage in case for some applications we need to lower the voltage. Then, of course, the ratio is below 1. And also everything in the white area would be a partial power converter. So there are plenty of opportunities to make different circuits and for different applications. And we started with photovoltaic energy systems. And the reason for this is that we can, by design, match the input and the output voltage quite easily, so that we can achieve maximum partial power ratio. This means the smallest power converter possible. So this is how a full power system would look like, and this would be the small power system, the partial power. And in this case, we achieved partiality ratios up to 10%. And here is one example of the topologies that you can later see in the room next to where we're having the exhibition. And this at that time achieved a world record efficiency of 99.8% because of the small losses. We then used this technology for green hydrogen production. Electrolyzers operate with DC current. The photovoltaic model is also with DC current. So using the DC-DC structure was straightforward. And here we also achieved very high efficiencies of 98.6%. This got the attention of EDF, a big energy company in France, and together with the Laplace Institute in Toulouse, we set out to innovate for green hydrogen production from offshore wind power. So we were commissioned to do research to replace traditional full power converters with partial power converters for these orange stages over here, one connecting the electrolyzer and another one connecting a backup battery. This is one of the topologies that we have patented and that we worked in this project. And here we can connect two separate electrolyzers, one here and one here, to a single DC input of the DC bus of the wind power farm after the rectification stage. And we achieved 99.5% efficiency. Here you can see that over the whole operating range, efficiencies are way above 99%. And the final example I bring to you is EV charging, electric vehicle charging stations. So electric vehicle charging stations usually connect to the grid through a rectifier and a DC-DC stage to regulate the current going to the battery. Again, here we replace this with the partial power technology, only processing a fraction of this. Because the battery in the electric vehicle has a wider voltage range than the photovoltaic system, we achieve here only a 30% of partiality ratio, but still a third of the volume, a third of the weight, and a third of the cost is actually a very good improvement. This was the first prototype we did, and we achieved 99% of efficiency. And we did a bunch of different circuits on this one, and one of these patents was licensed to the company Demax. Demax is a Chilean company that makes power converters for EV charging infrastructure in Chile to charge buses, like you see here in the Transantiago system, which is the metropolitan electric vehicle system in Chile. And we were commissioned not only just to license the patent, but also commissioned to make the first prototype for this charger, which each one is a 20 kilowatt building block. We put 7 of those in parallel to achieve 140 kilowatt, and in this way we can actually charge each bus with 400 kilowatts, 3 times that power. So we proved that the partial power concept is very useful for DC-DC applications. We not only tested it in the applications I showed you before, but also for LED drivers, which is the power electronics used for LED lights, and also for data centers. So if you're familiar with AI, you know that they are going to use more and more data centers. Those at one point have to convert from 48 volts to 12 volts and from 12 volts to 3.3 volts. In all those stages, we can use partial power converters and greatly increase efficiency and reduce the size and consumption of data centers in the future. We have achieved partiality ratios between 10 and 30%, so this means a tenth of the original volume and cost of a traditional power converter, up to 30%, and efficiency is way above 99%. So we really think that this can have a profound impact in energy transition technologies. If you imagine just in photovoltaics, there are over than 2 terawatts of installed capacity in the world. An increase in 2 or 3 or 4% in efficiency is a lot of energy. So with that, I thank you very much. Arigatou gozaimasu.